Hi, multivariable calculus. Ms. Deer back on the mic here. I just wanted to sort of go over what we know. So if we evaluate a line integral of work along a curve, if it's conservative, we can use the fundamental theorem of line integrals, find a potential function, plug in where we end up, x of b comma y of b, minus where we started, x of a, y of a. If it's not conservative, then we have to parameterize. So we would do f of x, y, ds, and turn this into the integral from a to b of f of x of t, y of t, times the magnitude of r prime of t, dt. And then if we're looking at a simply connected region, simply meaning it doesn't cross itself, connected meaning it's enclosed, then I have the closed integral around this region of m dx plus n dy, and we can evaluate this using Green's theorem, which this turns into the double integral over the region of the partial of n with respect to x minus the partial of the first one with respect to y. And I gave you a couple of examples of these. The next couple pieces we're going to talk about are sort of what are we looking at. So if I have a vector field that's defined by mi hat plus nj hat, and we're looking at the vector field if we evaluate this at a point xy. Well, one of the things we've been talking about is curl F. So curl F is, again, it's a vector. And what it's really asking is sort of to give, now remember, vectors have a magnitude and a direction. So the magnitude is really how fast, and then the direction is, and in what direction, that a region is spinning around a point parallel to k hat. So if I have curl F positive, it's going this way. If curl F, if it's negative, it would be going the other way. And so when we find curl F dot k hat, when we dot these together, we get the partial of n with respect to x minus the partial of m with respect to y. So whenever we have these, this is always going to give us curl F dot k hat, because all the other pieces will be nothing. So this is another way that we sometimes write out Green's theorem, and it gives us a way to sort of start to understand how curl F is working. So if I want to evaluate, let's do y cubed dx plus 3xy, let's do squared dy, and let's do this along the unit circle. Well, I can see that my partial derivative with respect to x is 3y squared. My partial with respect to y is 3y squared. Because this is a conservative field, then my inside of my double integral is 0, so we don't even need to do any evaluating. So there's going to be nothing accumulated. Accumulates. Another sort of cool result of Green's theorem is that we can see that whenever this piece is equal to 1, I'm just finding the area of the region. All right. So the next piece I sort of want to start to unpack for you is the idea of flux. So the outward flux. Now when we talk about vectors, they have to have a direction. So when we talk about the outward flux of a vector field, across a simply closed curve, across a simple connected curve that defines a region, then the outward flux is the divergence of the field over the region enclosed by the curve. So the flux, is sort of the rate at which, and I'm going to say fluid because we can all picture water, fluid is entering or leaving a region bounded by R, which is enclosed by a smooth curve C. So when we flux a field across C, we want to find the component of the field that is being projected onto the normal vector. So we say that flux of F across C. Well, this is going to be the projection of F onto the normal vector because we want to know how much is going through. So again, N is always pointing outward, and it's a unit normal vector. And so we're going to find this by finding m dy minus n dx, which turns into the double integral over the region of the partial of, with respect to x, plus dn dy. So this is called flux divergence form or normal form. Why is it called normal? Because it has to do with the normal vector. So we flux, again, you can think about if you had water flowing through this region, how much of it is flowing across the normal vector. The other way we're going to look at this is circulation curl. So now, instead of finding the component of the field on the normal vector, we can find the component of the field on the tangent vector. So this gives us, again, if we close it, we have a closed region. So now if we put this onto the tangent vector, this is going to be the m dx plus n dy, which turns into the double integral over the region of n dx minus dm dy. So this is called circulation curl because it has to do with what is flowing along, how much of the field is along the curve, which is very different than how much is normal to the curve. So these are sort of some alternate forms of Green's theorem and a way to start to understand what is curl, what is divergence. So if I give you a field, a not conservative field, so let's do x minus y I hat. Let's just do xj hat, and let's let R be bounded by the unit circle. So if I want to find the outward flux, so how much of it is on the normal vector? So we'll take the accumulation of F dot n along the curve, which we're going to write as the circulation of m dy minus n dx. So if we're going to put this over R, we're going to have to parameterize. So x is going to be cosine t, y is going to be sine of t. So our field, F, is going to turn into cosine t minus sine t I hat plus cosine t j hat. So plugging into here, we get the integral from 0 to 2 pi of cosine squared t dt, which is 1 plus cosine of 2t over 2 dt, which turns out to be 1/2 of 2 pi, which is pi. We could also take the double integral over the region of the partial of m with respect to x plus the partial of n with respect to y, which turns into the double integral over the region of 1 plus 0. So that's 1 dA. Because this is 1, this is just the area of our unit circle, which is pi times 1 squared, which is pi. So we get the exact same answer. If I look at circulation curl, that is around the boundary. So we can take the integral around this curve of f dot t ds, which is the circulation of m dx plus n dy, which is just the double integral of dn dx minus dm dy dA. So this turns into the integral from 0 to 2 pi of, I believe it was x minus y, so cosine t minus sine t times negative sine t plus cosine t times cosine t, all dt, which is the integral from 0 to 2 pi of negative sine t cosine t plus sine squared plus cosine squared, which is 1 dt, which turns into negative cosine t. Let's do cosine squared t over 2 from 0 to 2 pi, which is, plus t. So I get 1/2 plus 2 pi minus 1/2 plus 0. So I get 2 pi. And we could have obviously evaluated f dot dr, which would have given us the same integral. So just a couple more examples, if this helps you sort of picture the way this is going. If I want to evaluate along a closed curve, xy dy minus y squared dx, and let's look at my curve as a square cut by x equals 0, x equals 1, y equals 0, y equals 1. So this is my region. So I could take, turn this into Green's theorem, which turns into the double integral over the region of the partial of m with respect to x plus the partial of n with respect to y, which is the double integral of 3y. Let's go from 0 to 1, 0 to 1, nothing easier than a square region. Either letter we want, dx, dy, which turns into 3y dy, which is 3 over 2. We also could have let m is negative y squared and n could be xy. So around n dy plus m dx, this turns into the double integral over the region of dn dx minus dm dy, which is the exact same integral that we got here. So we're also going to get 3 over 2. So a couple of ways we're going to start to use these interchangeably. We're going to practice a lot more with Green's theorem. There is a way that we blow up Green's theorem into 3 space, which gives us Stokes' theorem and divergence theorem, which are going to be the end of this chapter. So hopefully this helps you with some of the problems in your homework and along with the other videos posted on Canvas.